So let's talk about quantum mechanics. It is, without a doubt, the most successful theory of reality we have ever devised. I mean, it just works perfectly. And yet, right at its very core, there's this puzzle. A puzzle so profound, it forces us to question the simple act of, well, of just looking at something. This is the measurement problem. And this quote from physicist Sean Carroll, it just captures the mystery perfectly. It sounds completely impossible, doesn't it? But here's the crazy part. A century of experiments has confirmed that it's absolutely true. So to understand how we ever arrived at this bizarre conclusion, we've got to go back to the moment quantum mechanics basically broke reality. All right, part one, a new kind of weird. To really get your head around quantum mechanics, you first have to appreciate how completely it shattered everything that came before it. Seriously, this wasn't some minor update. It was a fundamental rewrite of the rules of the entire universe. Okay, so think about the classical world of Newton. It was like a perfect clockwork machine. If you knew the position and momentum of every little piece, you could predict the future with absolute certainty. It was all deterministic. But the quantum world? It's a completely different ballgame. It's probabilistic. It doesn't deal in certainties, but in these weird, shimmering waves of possibility. And this is exactly why those old rules just had to go. Early models imagine the atom as a tiny little solar system. Cute, right? But according to classical physics, an orbiting electron should have radiated away all of its energy and spiraled right into the nucleus in, get this, 100th of a billionth of a second. Every single atom in the universe should have just instantly collapsed. Clearly, that didn't happen. Something was profoundly wrong. So what was the solution? Well, it was a radical new idea that replaced the old certainty of particles with the new uncertainty of probabilities. This is the wave function, and it is the mathematical heart of the entire quantum revolution. So instead of an electron being at one specific point, the wave function describes it as more of a smear of potential locations. It's not really a thing, but more like a cloud of possibilities for where that thing could be found. And this was the final, critical leap made by the physicist Max Born. He figured out the wave function basically gives you odds. You square its value at any point, and boom, that's the probability of finding the electron right there. Now you have to understand, this idea that nature is fundamentally based on chance, it was a huge shock. Even Einstein hated it, famously saying, God does not play dice. But this is where the math led. But this new probabilistic world actually created an even deeper puzzle. Because if reality is just a set of odds, what happens when we actually look? And this question leads us straight to the measurement problem, the central mystery we are still grappling with today. So here it is, the core question. The math describes this beautiful spread-out wave of potential. But every single time we run an experiment to find the electron, we find it at a single definite spot. That whole wave of possibilities just seems to vanish, replaced by one concrete reality. Why? This whole process is known as the collapse of the wave function. Before we look, there's a cloud of possibilities. After we look, there's a single certain outcome. But here's the kicker. The theory gives us no math for the moment of looking itself. That crucial step, the measurement, it's a complete black box. And that brings us to the absolute heart of the problem. What exactly is this special action called a measurement that forces reality to pick a single outcome from that wave of possibilities? Can a video camera do it? Does it require a conscious observer? The theory just doesn't say. The physicist John Bell drove this point home with this wonderfully sharp question. The idea that the universe's fundamental laws might require a physicist or even a bacterium to actually function is, to put it mildly, just absurd. And yet, this is the really uncomfortable place the standard theory leaves us. Now, I know you might be thinking this all sounds a bit philosophical and, well, kind of shaky. But here's the paradox. Despite this huge, gaping hole at its foundation, quantum mechanics is, and I am not exaggerating, the most powerful and precisely tested theory in the history of science. I mean, the theory works. It explains why the sun shines. It's the reason the semiconductor on your phone works. It underpins our entire understanding of chemistry, nuclear power, and the whole standard model of particle physics. Its predictions have been confirmed to just astounding levels of accuracy. We use it every single day. So how do physicists even handle this paradox? Well, one modern approach is something called quantum field theory. It proposes that the fundamental stuff of the universe isn't particles at all, but these invisible fields that permeate all of space: an electron field, a photon field, and so on. So what we perceive as a particle is just a tiny, localized vibration in one of these fields. And this gives us a new way to picture the whole quantum nature of reality. Think of a guitar string. It's continuous, but it can only vibrate at specific frequencies to produce distinct notes. In the exact same way, a continuous quantum field can only hold discrete packets of energy. And those little energy packets are what our experiments detect as particles. So, we have this theory that predicts things with near-perfect accuracy, but a foundational mystery about what it all means. This brings us to the final part of our story, the ongoing and very unfinished quest to figure out what quantum physics is actually telling us about reality. This quote, inspired by science writer Adam Becker, just frames the current situation perfectly. You see, for decades, many physicists kind of adopted a shut up and calculate attitude. But now, more and more of them are returning to these foundational questions, really unsatisfied with not knowing what our best theory of the world truly means. And here's the key takeaway. After nearly a century, the experts still don't agree. There are all these competing interpretations, like many worlds or Bohmian mechanics, that all try to solve the measurement problem, but not a single one has achieved a consensus. The debate is as alive and as heated today as it was 100 years ago. And so that leaves us with this one last, really provocative question. How can a theory be so incredibly good at predicting what will happen, while we remain so fundamentally divided on what is actually happening? This is the strange, beautiful, and, the deeply unsettling puzzle at the very heart of quantum mechanics.